Apart from finding the area underneath a curve, there are a lot of smaller applications for integration. One of the main ones is finding the average value of a function. It's pretty self-explanatory what that essentially means, but essentially it's just the average level of a function, and it takes into account the negative and positive regions as well. So the formula for it is the integral, the definite integral of the function from a to b, a lower bound, b upper bound, but then we divide by the difference between the lower and the upper bound. So we have this example here where we have f of x is equal to x squared minus 1/2. And I've used this example specifically because you can see from x equals 0 to x equals 1, that's what we're trying to find our average value for. But you can see the y value at the lower bound is negative 1/2. The y value at the upper bound is positive 1/2. And I've used this example on purpose because a lot of people would see this and think that the average value is going to be 0, because you can see the midpoint between negative 1/2 and positive 1/2 is obviously 0, or at the x-axis. But in this case, you can't actually do that because now we're kind of confusing midpoint and the average value, which is slightly different. And I'm going to show you with calculations that it is different and then explain why. So if we want to find the average value of this function, what we do is we just apply this formula here. So we go 1 over and then 1 minus 0 because they're our x bounds. The x upper is 1, x lower is 0. Don't confuse it with the y bounds. And then we go integral from 0 to 1 of x squared minus 1/2 dx. And then we just go ahead and evaluate this. Obviously the 1 divided by 1 minus 0, that has no effect in our equation, so that makes it a bit easier. And then we don't need integral anymore. We just go straight to definite integral. X squared becomes x cubed over 3. 1/2 becomes 1/2 x. 0 to 1. And again, 0 to 1, very nice numbers to substitute in when we're doing definite integrals. So we go 1 cubed over 3, and then minus 1/2. And then when we substitute in 0 to everything, we end up getting 0. So our final answer is 1/3 minus 1/2. If you want to do this a long way, you make a common denominator. So you go 2 over 6 minus 3 over 6, which is negative 1/6 as our final answer. And you might be thinking, oh, we have a negative value. What essentially does that mean? Or what exactly does that mean when looking at our curve and the properties of it? And you can see in this case that, yes, a lot of people would see the midpoint as y is equal to 0 and think that's our final answer. But in this case, what you can actually see, if I change colors, is that this area here, or like the density of this curve, is lower than this curve here. And that's just due to the nature of our parabolic curve. We know a parabolic curve goes something like this, where you start off more shallower, and as you go further and further, you go steeper. And that's just due to the squared nature of functions. Because you can imagine, if we just look at a basic case of a hyperbola, we start off at 0, 0, then we go through 1, 1, and we go up from there. And actually this is, again, basic case, y is equal to x squared. If we go from x equals 0 to 1, what you can see is that the curve is actually very shallow, and that's because when you square a number that's less than 1, it actually gets smaller. So for example, if you do 0.8 multiplied by 0.8, you get 0.64, which actually causes the number to be smaller. But if you go beyond x equals 1, for example, if you go x equals 2, you square that number, it actually gets bigger. And that's what causes the parabolic nature of this curve here, where it goes shallow at the start and steeper at the top. And you might be thinking, what does that have to do with my average value? It's because if this curve is shallower at the bottom, there's more numbers here than there are here. And that actually causes the average value to be less than y is equal to 0, or less than the midpoint. It's because the midpoint is here, but you can see the curve is kind of lower compared to how high this curve is here after the x-intercept. And that's why in this case, or in most cases, the average value is going to be different than the midpoint.